Hi friends, this is Rashekar, a GET faculty for electrical machines. In this video, we are going to discuss about harmonics and non-linearity effect in transformers. First of all, what is harmonics? What is the definition of harmonics? Can you tell me what is the definition of harmonics? Harmonics nothing but the integer multiples of fundamental frequency. Integer multiples of fundamental frequency is called the harmonics. Nothing but, for example, my fundamental frequency is 1, then its integer multiples nothing but 2, 3, 4, 5, 6, 7, 8, 9, and so on. These all are called harmonics. But in generally, for symmetrical waveforms like a sinusoidal symmetrical waveforms, for all the symmetrical waveforms, even harmonics are arithmetically eliminated. Then the remaining harmonics are 3, 5, 7, 9, 11, 13, 15, 17, 19, and so on. These are now our harmonics. These harmonics are divided into three groups. One is the 6n-1, and other one is the 6n+1, and other one is the triple n harmonics. These are the three groups of harmonics. For example, 6n-1 group is nothing but 6 into 1, 6 minus 1, 5, and 6 into 2, n is equals to 1, 2, 3, substitute there, n is equals to 2, 6 2s are 12, 12 minus 1, 11, 6 into 3, 18 minus 1, 17, and so on, 5, 11, 17, and so on. These are called 6n-1 harmonics, or fifth group harmonics. And what about 6n+1? 6 into 1, 6, 6 plus 1, 7, 6 into 2, 12, 12 plus 1, 13, and 19, and so on. Nothing but 7, 13, 19, and so on. These are called 6n+1 group harmonics, or seventh group harmonics. And what about remaining triple n? 3 into 1, 3, 3 into 2, 6 eliminated, 3 into 3, 9, and 12 eliminated, 15, and so on. This is 3, 9, 15, and so on. These are called triple n harmonics. The total harmonics are divided into three groups. In this, generally, the fundamental harmonics having some principles. What is that principle? The fundamental harmonics. Fundamental frequency. We have a three harmonics, for example. We have a three phase, for example, phi 1, phi 2, phi 3. Phi 1 is equals to phi m into sine omega t. Phi 2 is equals to phi m into sine omega t minus 120 degrees, the second phase. And the third phase, phi m into sine omega t minus 240 degrees. This is the three phases of fundamental. Nothing but one phase at 0 degrees, and another phase at 120 degrees, and the another phase at 240 degrees. each phase displaced by 120 degrees, each phase displaced by 120 degrees, and each phase currents I1, I2 and I3, sum of three phase currents is equals to 0. These are the fundamental principles. What is that? The fundamental principles. The three phases are displaced by 120 degrees each other, and the sum of three phase currents is equals to 0. These are the fundamental principles. Now, let's check the 6n minus 1 harmonics and 6n plus 1 harmonics and triple n harmonics, how they are different from fundamental. How they are different from fundamental. Let's check it. Okay, let's check it. How they are different from fundamental. Let's check it once. Let's check it once. See here. I'm seeing here for 6n minus 1, 6n plus 1 and triple n harmonics. First of all, 6n minus 1, in that I am going to analyze fifth group harmonics. Fifth group harmonics or fifth order harmonics. Fifth order harmonics. So fifth order harmonics, I'm saying here, for example, phi R phase and Y phase and B phase. These are the three phases. Do you know where the R phase being located? In generally, we know the R phase of the fundamental is located at 0 degrees. The Y phase is located at 120 degrees and B phase is located at 240 degrees. But our R phase of the fifth order harmonics is located at 0 multiplied with phi, so 0 degrees. Because this is 0, this is fifth order, that's why multiplied with phi. And next one, Y phase. What is Y phase? Actually 120 degrees, but this is multiplied with phi, nothing but 600 degrees. 600 nothing but if you started here, 360 completed and remaining 240. This is 600 nothing but 240 degrees. And what about phi B phi? Actually B phase at 240 degrees, but this is fifth group, that's why fifth 5 times. So what is the answer? 1200 degrees. 1200 nothing but once 360 completed, second time 360 completed, and third time also 360 completed. So if third time also 360 completed, then the remaining is only 120 degrees. Remaining is only 120 degrees. So the R phase of the fifth order is located at 0 degrees. Located at 0 degrees. And Y phase is located at 240 degrees. And B phase is located at 120 degrees. Of course, these three phases also displaced by 120 degrees each other. But see here R, Y, B phases are like this. R, Y, B phases are like this. R, Y, B phases are like this. But here, see, this R, Y, B phases are in opposite direction. R, Y, B phases are in opposite direction. So the fifth order harmonics follows the fundamental rules. These are also follows the fundamental rules, but in which direction? In opposite direction, not in clockwise direction. This follows the fundamental rules in anti-clockwise direction. That's why fifth order harmonics are also called as Negative sequence harmonics. Negative sequence harmonics. Fifth order harmonics are also called as negative sequence harmonics because these are follows the fundamental rules in reverse direction and each phase displaced by 120 degrees. That's why IR phi plus IY phi plus IB phi is exactly 0. No problem with fifth order harmonics. The fifth group harmonics are negative sequence harmonics because this follows the fundamental rules in reverse direction. This is about the fifth order harmonics or negative sequence harmonics. And next, let's go for seventh group or 6n plus 1. 6n plus 1 are seventh order harmonics. Now I want the flux of R phase. We know actually R phase at 0, but we have to multiply it with 7, again 0 degrees. Next, what about Y phase? What about Y phase? Actually Y phase fundamental 120 degrees, but now multiplied with 7. If you calculate this, you can get 120 degrees only. And B phase 240 multiplied with 7. If you calculate like this, after all complete solution, you can get 240 degrees again. Nothing but the seventh order harmonics, R phase located at 0 degrees, Y phase located at 120 degrees, and B phase located at 240 degrees. Each phase displaced by 120 degrees as usually. And this follows the fundamental rules in clockwise direction only. RYB. This follows the fundamental rules in counterclockwise direction. But the seventh group harmonics follows the fundamental rules in clockwise direction only. That's why the seventh group harmonics are also called as positive sequence harmonics. Positive sequence harmonics. These are also called as positive sequence harmonics. This is positive sequence harmonics and this is negative sequence harmonics. And here also IR7 plus IY7 plus IB7 exactly 0. No problem with seventh order harmonics also. So the fifth order and seventh order harmonics follows the fundamental rules and sum of the three phase currents is equals to 0. Of course, fifth order in counterclockwise direction, seventh order in clockwise direction. That's why fifth order harmonics are called negative sequence harmonics and seventh order harmonics are called positive sequence harmonics. Is it okay? Right? Right. Next one. Let's go for triple N harmonics. Triple N harmonics. Let's go for triple N harmonics. Now we have to calculate for triple N harmonics. See here. Now triple N harmonics. Triple N harmonics. So calculate phi R3. Phi R3 generally R at 0, but this is triple N, that's why multiplied with 3. So 3 into 0 again 0 degrees. So my R phase is located at 0 degrees. And next one Y phase phi Y3. Actually Y phase is at 120 degrees. But this is triple N, that's why multiplied with 3, nothing but 360 degrees. 360 degrees, nothing but 0 degrees. Again, the Y phase also located at 0 degrees. Y phase also located at 0 degrees. Now, let's go for B phase. Actually B phase at 240 degrees. But this is triple N, that's why multiplied with 3. So, 243 is 720 degrees. 720 minus nothing but 360, 360. 360, 360. So 720 also nothing but 0 degrees. 0 degrees. Nothing but the B phase also located at 0 degrees. All the phases are located at 0 degrees. There is no phase displacement. There is no phase displacement. All the phases are located at 0 degrees. So these are doesn't follows the fundamental rules. Doesn't follows the fundamental rules. The third harmonics doesn't follows the fundamental rules. There is no phase shift of 120 degrees. And also here the IR3 plus IY3 plus IB3 not equals to 0. This doesn't follows the fundamental rules. This is the problem. And this triplen harmonics is also called zero sequence harmonics. Zero sequence harmonics. And these are also called co-phasor harmonics. Co-phasor harmonics. Co-phasor harmonics because all are in same phase. Are triplet harmonics. These are also called triplet harmonics. These are zero sequence harmonics. There is no any sequence for this. So this triplet harmonics doesn't follow the fundamental rules. These are the richest harmonics in our transformer. Compared to all harmonics, the triplet harmonics are the richest harmonics for transformer. Triplet harmonics are the richest harmonics for transformer. The EMF equation induced in the windings is the shape, wave shape of the EMF is mainly depends on triplet harmonics. It affected more and more. The wave shape of the EMF equation is affected by the triplet harmonics only. Triplet harmonics only. Are you getting or not? Okay. Right. Now harmonics completed. Now non-linearity. Generally in this harmonics, I said you the triplet harmonics are richest harmonics. Triplet harmonics are richest harmonics. This triplet harmonics decides the EMF waveform. For example, if the winding is in delta, the transformer winding is delta connected. If the transformer winding is delta connected, this is my transformer, this is delta connected, and this is my source. I am giving the supply to like this. For example, this is like this connected. This is VA, VB, and VC, and these are the transformer. This is, for example, EA1 plus EA3 plus EA5 and so on. And this is EB1 plus EB3 plus and so on. And this is EC1 plus EC3 plus and so on like this EB1, EB2 like this. For example, I connected this source voltage to our transformer, which is a delta connected transformer. Delta connected transformer. I connected for a delta connected transformer. Here I have a harmonic component also. Fundamental component and harmonic component. Actually, the EA1 and EB1 and EC1 balanced by the source voltages, VA, VB and VC. But this EA3 and EB3 and EC3 not balanced. These are not balanced. These are not balanced, and these produces the third harmonic currents. These produces the third harmonic currents, which gives a closed path in delta. It provided by the closed path. The delta provides the phase-to-phase closed path in delta. Phase-to-phase closed path for third harmonic currents. Phase-to-phase closed path for third harmonic current. Phase-to-phase closed path for third harmonic current. So here we have a third harmonic current closed path between phase to phase. Now here the I mu is a peaky wave. I mu is a peaky wave. Then flux and EMFs are sinusoidal. Flux and EMFs are sinusoidal. Here I mu is a peaky wave and flux and EMFs are sinusoidal. How it is? Generally, here the I mu is a peaky wave, but the flux and EMFs are sinusoidal when the transformer winding is delta connected. When the transformer winding is delta connected, then to get the sinusoidal EMF, the magnetizing current should be a peaky wave. Magnetizing current should be a peaky wave. This is the effect of third harmonics. Effect of third harmonics in delta connection. For example, if the transformer having star connection, then how it was? If the transformer having star connection, let's see, if transformer having star connection, for example, if my transformer is having star connection like this, this is my star connected transformer. Of course, here also I have EA1 plus EA3 plus and so on. Here EB1 plus EB3 plus and so on. Here EC1 plus EC3 plus and so on. These are the EMFs produced in the transformer, fundamental and third harmonics, EA and EB and EC, like this. Here also, this EA1, EB1, EC1 balanced by the supply source VA, VB, VC. But EA3, EB3, EC3 not balanced by the supply source. But it doesn't produce the third harmonic currents. This star connected winding doesn't produce the third harmonic currents, because no closed path between phases, for third harmonic currents. In delta, it produces closed path and it produces third harmonic currents because it provides the closed loop for third harmonic currents between the phases. But here the star connection doesn't produce the third harmonic currents because there is no closed path between the phases. Hence, here I mu is sinusoidal. Here I mu is a sinusoidal. When I mu is sinusoidal, the flux is flat tapped. The flux is flat tapped or trapezoidal. Here I mu is sinusoidal and flux is flat tapped or trapezoidal. Then EMF is not a sinusoidal. EMF is maybe a peak value, peak wave. In star connection, the EMF is not a sinusoidal because here it doesn't produce the third harmonic currents. We have only sinusoidal I mu. We have only sinusoidal I mu. If it produces, for example, this is I mu actually, this is for fundamental. If it produces third harmonics, or if it produces third harmonics like this, then it is added here. This is added here. If this is added here, how the waveform? If this is added here, the waveform is like this. This is called peaky wave. In delta, we have a third harmonic currents. Then this is added to sinusoidal. Then our I mu is a peaky wave. If the I mu is a peaky wave, then the flux is sinusoidal. But in star connection, there is no third harmonics. So the I mu is sinusoidal. If I mu is sinusoidal, then the flux is flat tapped. The flux is flat tapped, and the EMF is peaky wave. And the EMF is peaky wave. It is not sinusoidal, it is a peaky wave. So the conclusion is that in transformer, if we have a delta connection, we have a third harmonics. In star connection, if my transformer having star connection, then there is no third harmonics path. Here I mu is a peaky wave. Here I mu is only sinusoidal. Here EMF and flux both are sinusoidal. Here EMF and flux both are sinusoidal. But here EMF and flux not a sinusoidal. Because there is no third harmonics path. Then how we can get a sinusoidal voltage? Sinusoidal EMF in star connection. How? In delta we have a closed path. But in star there is no closed path. If there is a closed path for third harmonics, then we can get the sinusoidal EMF. How we can get the closed path? By providing the neutral grounding. If the star is neutrally grounded, then the third harmonics takes the closed path. When the third harmonic currents flows in the phases, then the I mu is a peaky wave. Then the EMF and flux is a sinusoidal waves. When the star is neutral grounded. Then I mu is a peaky wave, then flux and EMF is a sinusoidal. This is the effect of harmonics. Are you getting or not? So simply, the main conclusion is that if the third harmonics present in the transformer, then the EMF is sinusoidal and I mu is a peaky wave. And next one, non-linearity. For example, ideal and practical condition. practical condition. In ideal condition, the BH curve is, in ideal condition, the BH curve is linear. But in practical, the BH curve is non-linear, perfectly non-linear. This is not a linear. Yes or no? Yes or no? Here, hysteresis losses is equals to 0, but here hysteresis losses not 0. Here, even though I mu is sinusoidal, flux and EMFs also sinusoidal. Even though I mu is sinusoidal, flux and EMFs also sinusoidal in ideal condition. But practically, if I mu is a sinusoidal, then EMF is not a sinusoidal. EMF is not a sinusoidal. It may be peaky wave. If I mu is peaky wave, then the EMF is sinusoidal. How we can get the I mu is peaky wave? Either by using delta connection or by using star with neutral grounding connection. We can get I mu is a peaky wave. Then the EMF is a sinusoidal. Otherwise, EMF is not sinusoidal. This is due to non-linearity. This is simply the overview of harmonics and non-linearity concept. Are you okay? Understood? Right? Thank you, sir.